All right, we're going to continue on chapter 6. We're going to manipulate our thermochemical equations. All right, so remember that is a balanced chemical reaction that has a delta H value. All right, so if you're going to multiply through by 2, so if you multiply everything through by 2, you must also multiply your delta H by 2. If you're dividing it by 2, the whole equation, then the delta H must be divided by 2. So whatever you're doing to the reaction, you also have to do to the delta H. When you reverse a reaction, that means your reactants become products, your products become reactants. Your delta H is reversed. All right, so if you have reactants, all right, so on the left, by convention, that is your reactants. And then on the right, always your products. If this reaction releases heat, that means heat is a product. This would be an exothermic reaction. All right, so if you run your reaction and heat is released, you have an exothermic reaction. And so heat is considered a product. It is something that is given off. If you reverse that reaction, all right, it's hard to do it this way because you're not going to write reactants. You're not going to write reactants on the right and products on the left. But if you reverse it, what happens is then you have heat as a reactant and going to products. So even when you reverse it, it's still anything on the left side of the arrow is called the reactants. Anything on the right is called the products. All right, but if you have heat as a reactant, then heat is absorbed and you have an endothermic reaction. All right, so for all endothermic reactions, heat is a reactant. All right, and so exothermic reactions, you hold the flask, it's very hot. If you have an endothermic reaction, you hold the flask, it is very cold. All right, so here is a thermochemical reaction right here. So here is a balanced chemical reaction, and it gives you the delta H. All right, so the delta H is positive. If it's positive, they don't put plus there. It is understood that it is positive. If it's negative, they must put the negative. When your delta H is positive, that means you are endothermic. All right, and so this is an endothermic reaction. All right, so if you reverse it, then it's going to be an exothermic reaction. So when you reverse this, you just write your products are now reactants. So you have CO plus 3H2, and that gives you CH4 plus H2O. And now your delta H, when you write the thermochemical reaction, is a negative 206 kilojoules. All right. So on this reaction, this is written as a thermochemical reaction. There is a semicolon here, and then you give the delta H. They could have written in the heat. They could have written over here plus 206 kilojoules. That would be the same thing. That would not be a thermochemical reaction because by definition, that means you have a semicolon and you list the delta H. But you could write this same reaction as your CH4 plus H2O plus 206 kilojoules yields CO plus 3H2. Up here, it would be written in the reverse reaction where you would have your CO plus your 3H2 plus CH4 or yield CH4 plus H2O plus, on this side now, it's exothermic, so plus 206 kilojoules. So if they write the heat as a product, you have to know that means you have a negative delta H. If they write the heat as a reactant, you have to know that that is a positive delta H. All right, so it says here in this question, which of the following are exothermic? It is any of these reactions where the CO and the H2 are reactants. All right, and so the only one, well, no, there's more than one. All right, so this is exactly what I wrote up above. All right, so that one is exothermic. Your delta H here is negative 206 kilojoules for this reaction. Note the next one down, D. What we did was we took part C and we multiplied it by 2. All right, and so the delta H, whatever you do to the reaction, you also have to do to delta H. All right, and so what we did was we took this reaction and we multiplied it by 2 from C down to D. That means you have to multiply the delta H by 2, and so that is negative 412 kilojoules. It is still exothermic. All right, so the first reaction, part A, that's exactly what was given. This delta H is exactly what is given. This is delta H of 206 kilojoules. All right, endothermic. And then you note here that all they did from A to B is they took part A and they multiplied it by 2. And when you take part A and multiply it by 2, you have to multiply the delta H by 2. And so the delta H here is equal to a positive 412 kilojoules. So you have A and B are both endothermic, C and D are both exothermic. So you have to know if you multiply a reaction by a factor of, say, 2 in this case, you got to multiply delta H by 2. If you reverse the reaction, you have to change the sign of delta H. The positive becomes negative. All we did from A down to C is reverse the reaction. All right, B down to D, also we reverse the reaction. You reverse your reaction, you change your sign of your delta H. All right. All right, here's another thermochemical reaction. All right, so here what we can say in this balanced chemical reaction is 1 mole of S8 reacts with 8 moles of O2 to produce 8 moles of SO2. And when 1 mole reacts with 8 moles to give 8 moles, then your delta H is negative 2.39 times 10 to the third kilojoules, exothermic reaction. All right, so now it says write the thermochemical equation for the dissociation of 1 mole of sulfur dioxide into its elements. That means sulfur dioxide into its elements, which are sulfur and oxygen. All right, and then the key here is 1 mole, not this reversed. This reversed would be 8 moles of sulfur dioxide into its elements. The question asks for 1 mole. When the question asks for 1 mole, then you're going to have to use fractions. All right, if it says to balance this, you should not use fraction. If it says balance this, but you must use 1 mole of sulfur dioxide, then you must use fractions. All right, so in order to get 1 here, all right, we have to divide the whole thing by 8. So everything here has to be divided by 8, including your delta H. All right, but we want a dissociation. We want SO2 to go into S8 and O2. That means we also have to reverse this reaction. So we have SO2, 1 mole. It says in the problem it must be 1 mole. That has to be a 1. All reactions must be balanced. All reactions do not have to have integers, but they all must be balanced. All right, so if we have 1 mole, we have to then have 1/8 of a mole of S8. And we must have 1 mole of O2. All right, so this, if I would just reverse this reaction, then I have 8 SO2s going to S8 plus 8 O2s. My delta H for this is a positive 2.39 times 10 to the third kilojoules. All right, so when you reverse it, it becomes positive. But now we have to divide it by 8. And so we have 2.39. We have to divide that by 8. All right, so you've got your... So so 2.99 times 10 to the second kilojoules, or 299 kilojoules. All right, so then you have your semicolon. Delta H for this is equal to, now we reversed it, and so it is endothermic. So that is 2.99 times 10 to the second kilojoules. All right, so this is as hard as this can get. You have to reverse it, which means you have to change the sign. You had to multiply through by 1/8. That means you had to multiply your delta H by 1/8. All right, and so that is how that is done. It will show that here. All right, reverse it, and that changes the sign. And then you have to divide everything by 8 or multiply through by 1/8, however you want to see it. That's the same thing. All right, and so then when you divide that by 8, you get 299 kilojoules endothermic. All right, so now we're going to be maybe not exactly 1 mole, maybe not exactly 8 moles, maybe 1.2 moles, 25 grams, whatever. All right, so your starting units, whenever you have starting units, you're going to always have to convert them to moles, because that's how we write a chemical reaction. Those coefficients are moles. All right, so whatever you're given, you have to convert to moles. All right, whether it is a mass. All right, so if you're given a mass, you have to convert that into moles. All right, and the equation is, when you do your molar mass, that is mass per mole. All right, so if you want to solve this for mass, all right, you solve it for mass. Well, we're going to solve it for moles because we want to find moles. You have to take your mass and divide by your molar mass in order to get moles, or you simply do the units. So grams divided by grams per mole, the molar mass. All right, so you will take your mass divided by molar mass. That's going to give you moles. You can be given a concentration of something. Usually an acid is given as a concentration. Molarity times volume is equal to moles. But remember, molarity is moles per liter. So your volume has to be in liters in order for this to give you moles. Units are very important. All right, so you're going to have to go to mass into moles, or molarity into moles. Once you have moles, you use your balanced chemical reaction, and then you can also use your kilojoules per mole. So if we look at the next problem, and we're doing the same thing, we're going to do our sulfur in air. All right, so we have S8 plus 1. Now we'll go with O2, 8 of them. Now we get 8 SO2s. All right, so they have to give you this equation. So they have to give you the equation that is right there. So we have our equation. That's the one. Well, you can't see it now. So S8 plus 8O2 goes to 8 SO2s, and with the delta H. So this is the problem, negative 2.39 times 10 to the third kilojoules. So they give you this in the problem. All right, so now we're not doing 1 mole of S8. We're not doing 1 mole of O2. We're not doing 1 mole of SO2. We're doing 15 grams of sulfur. All right, so we have 15 grams of S8. All right, so what we have to see is that if we had 1 mole of S8, we get negative 2.39 times 10 to the third kilojoules of heat. All right, released. So we have to convert our 15 grams into moles. So you have your 32.06. We can use the other equation too if we wanted to, because that one would be easier for me. The one we just did had 1/8 of S8 plus O2 goes to SO2, and that had a delta H, and that one is exothermic, minus 299 kilojoules. All right, this equation and this equation are exactly the same. They are per mole. All right, so basically it's like that's 1 mole. This is 1/8 of a mole. Here's for 8 moles. Here's for 1 mole. These are differ by a factor of 8 that we just calculated. All right, so I can take my 15.0 grams of S8, and then I have to divide by the molar mass, which is 32.06 times 8. grams per mole because there are 8 S's in S8. That's moles of S8. All right, and it doesn't matter which one you use. If I use the one on top, I see I have 1 mole of S8. All right, balanced chemical reaction up here, 1 mole of S8, and that releases 2.39 times 10 to the third kilojoules. If I put 1/8 and I put negative 299, it would give me exactly the same answer. So moles of S8 cancel moles of S8, grams of S8 cancel grams of S8, and we would have our answer in kilojoules. All right, and that would be how much heat is released, or in this, they use the word evolves. That's how much heat is released. It is exothermic. You're burning something, you're going to be giving off heat. All right, so that's going to be, this math is needing a calculator. All right, so 32 times the 0.06, 32.06 times 8, that gives you 256.5 grams per mole. All right, then you take that times your 15, that cancels, and then your 1 mole of S8 releases 2.39 times 10 to the third kilojoules. All right, so this releases 1.40 times 10 to the second kilojoules, or it releases 140 kilojoules of heat. So you can say negative 140 kilojoules, that's what Q is. It releases 140 kilojoules. That is also saying negative in words. When you say releases, that means exothermic. That means a negative Q value, a negative delta H value. All right. All right, daily energy requirement for a 20-year-old man weighing 67 kilojoules is 1.3 times 10 to the fourth kilograms. That's kilojoules. All right, for a woman weighing 58, daily requirement is 8.8 times 10 to the third. If all the energy were to be provided by the combustion of glucose, how many grams of glucose would have to be consumed by the man and the woman per day? All right, so what we're doing is we're taking our 1.3 times 10 to the fourth kilojoules. All right, that's our Q value. We're going to see, all right, and we want how many grams of glucose. So here's your glucose. They have to give you this balanced chemical reaction, thermochemical reaction. We know that we can get 2.82 times 10 to the third kilojoules for every mole of glucose. All right, and for the man, it is 1.3 times 10 to the fourth kilojoules that is required. All right, so we would write that we need 1.3 times 10 to the fourth kilojoules. So a 20-year-old man needs 1.3 times 10 to the fourth kilojoules. All right, and this reaction says that we can get, that we release, so we can get from this combustion of glucose, we can get 2.82 times 10 to the third kilojoules for every mole of glucose, C6H12O6. All right, but it didn't ask how many moles of glucose, it asked for the grams. And so all we need to do is find the molar mass of glucose, 72, 12, 84, 6, 180. So 180 grams per mole. All right, and then that will give us the grams of glucose. The only difference for the woman is we have to put, instead of 1.3 times 10 to the fourth, we put 8.8 times 10 to the third. And we will get the grams in glucose that need to be consumed per day. All right, so we take, for the 20-year-old man, that is the energy required. We get 2.82 times 10 to the third kilojoules for every mole of glucose. There's the molar mass of glucose, 180.2. And when you push the buttons, you get 830 grams of glucose required. So this is 2 sig figs, so it should be written as 8.3 times 10 to the second grams of glucose. All right, so again, for the woman, we're just going to change this number. Everything else is going to be the same. So we change that to our number given in the problem, 8.8 times 10 to the third. We still get 2.82 times 10 to the third kilojoules per mole, and it's still the molar mass of 180.2. We push the buttons, and we see that that is 560 grams of glucose to 2 sig fig, should be written as 5.6 times 10 to the second grams C6H12O6. All right, so what you need to see from this is that your delta H here is used in your mole ratio. All right, so it says that 1 mole of glucose burned releases 2.82 times 10 to the third kilojoules. It could have given you something else. It could have said oxygen. Well, we only had, 6 grams of oxygen. How much glucose can be burned? Or how much heat is released if we only have 6 grams of glucose? You have to convert that to moles. And you see that you would release 2.82 times 10 to the third kilojoules for 6 moles of oxygen. All right, so that is the same mole ratios that you would use before. 1 mole glucose reacts with 6 moles oxygen to produce 6 moles CO2 and 6 moles H2O. When that reacts in the mole as listed, 1666, then you have released 2.82 times 10 to the third kilojoules. If you multiply it by 2, you multiply the delta H by 2. If you divide it by 2, you divide the delta H by 2. If you reverse the reaction, your delta H changes from a negative to a positive. All right, so here we're going to measure heats of reaction. All right, so we're going to talk about raising the temperature. Okay, so we're going to look at a temperature change to measure the heat of reaction. So an exothermic reaction is going to get hot. We're going to measure that by using a thermometer. If we do an endothermic reaction, it is going to get cold. Again, we would measure that by using a thermometer. All right, so we're going to talk about the molar heat capacity and the specific heat. All right, so it is the quantity of heat needed to raise the temperature of the sample of substance by 1 degree Celsius. That is your heat capacity. When you're doing molar heat capacity, it is for 1 mole. All right, so how much heat is required to raise the temperature of 1 mole of the substance 1 degree Celsius? When you're talking about, so that's molar heat per mole. When you're doing specific heat, all right, that is per gram. All right, so that is per gram. And so your specific heat is S. All right, and for water, it is 1.000 calorie per gram degree. So that is your specific heat of water. It takes 1 calorie to raise 1 gram of water, 1 degree Celsius. All right, so note here that I was very, very, very adamant that you must be working in Kelvin. This is where people get in trouble. Here it says Celsius or Kelvin, all right? Because it is going to be a change in temperature. We're going to raise the temperature 1 degree Celsius. All right, and so when we're talking about changing a temperature, we're talking about a delta T. So that is your temperature final minus temperature initial. That is your delta T. When you have a delta T, you can work in Celsius or you can work in Kelvin. All right, when you have just a T, must be Kelvin. All right, so you can convert everything to Kelvin and it will never be wrong, but you might be doing a little extra work. I would recommend that. Any temperature you're given, you must immediately convert it to Kelvin. But you also should know that your delta T, it doesn't matter if it is in Celsius or Kelvin. So let's do an example. Let's say I'm going to do an exothermic reaction and it goes from 25 degrees Celsius to 35 degrees Celsius. All right, so I do my delta T. Final, 35 minus 25. My delta T is 10. All right, so your delta T, final minus initial, is 10 degrees Celsius. All right. But I told you, convert everything into Kelvin. All right, so you have your Kelvin. So I see my 25, I get rid of it, and I change that to 298 Kelvin. I added 273. Then I get rid of my 35, and I have 308 Kelvin. So then I do my delta T, and I take my 308 minus my 298. I get 10 Kelvin. So your delta T, it will be the same whether you're using your Kelvin or you're using your Celsius. However, if they give you a delta T and they say your delta T is 10 degrees Celsius, all right, you need to know that delta T means it changed by 10 degrees. It is not actually a temperature. Delta T is not a temperature. It is how much it changed. All right, so if you say you're going to add 273 to this, and now my delta T is 283 Kelvin, well, that is wrong, because this is not a temperature. That is a change in temperature. That's how much it changed. So you cannot convert that. You have to know it's the same. If you want to convert it, then you find your delta T, the numbers you used, you plug those in, and then you get your delta T in Kelvin. And every time you do that, you'll see that your delta T in Celsius and your delta T in Kelvin are identical. And so that's why it says when you're changing the temperature, it's going to go up by 1 degree Celsius, or you could use 1 degree Kelvin because, and you see in this example, going from 25 to 35, that it is both a 10 degree change. 10 degrees Celsius or a 10 Kelvin change. Anytime you have just T in an equation, it must be in Kelvin. If you have a delta T in an equation, you can leave it in Celsius and get a delta T, or you can convert those both to Kelvin and get a delta T. Those numbers will be identical. All right, so here's all your equations with a delta T. All right, again, if it's just a, boy, that is the wrong T. That is a capital T. All right, so that is a capital T. If you have a lowercase t, that is time. If you have a capital T, that is temperature. So those are capital T's. That is a change in temperature. All right, so your heat capacity is a C delta T. All right, and so your Q is always in energy units, which the SI unit for energy is the joule, and so we're going to get this in joules. So your heat capacity is going to be in joules per, usually it's written as degree, but it could be best to say joules per degree change, and then you have times your degree change. This can be Celsius or Kelvin. This can be Celsius or Kelvin because it is a delta T. Delta T can be Celsius or Kelvin. It's the same number. All right. The reason why it says it can be this or this, it's not two different numbers. It is the same number. If you do a delta T and you get Celsius and you get instead you want to go to Kelvin, if that's two different numbers, you did it wrong. The delta T can be in Celsius or Kelvin because it's exactly the same number, as we saw in our last example of going to 25 to 35. Your delta T is 10, whether you do it in Celsius or Kelvin. All right, so when you have your heat capacity, all right, so that's per gram. So now you have your Q, and your S value is your, well, if we had before 4.184 joules is equal to 1 calorie. All right, so if we're doing it in joules, you have a constant for water. If we're looking at water, the heat capacity of water, 4.184 is joules per gram degree times grams. Mass is in grams here. And again, you need to know the units because all the other equations, mass had to be in kilograms to give the correct units. Here, it has to be in grams to give you the correct units. And of course, your delta T, we talked about it enough. Degree change. And so that, again, will give you Q in joules. So units are extremely important. All right. So if you want to measure the heat absorbed or released in a chemical reaction, you use in the lab a calorimeter. we use a coffee cup calorimeter. All right, so it basically, we don't want any heat being lost to the surroundings, so we use an insulated cup, and a nice styrofoam cup works very well to keep that heat inside of the container. All right, so you have your thermometer to measure the heat that is going to be, in this case, released, because we're going to add a strong acid, HCl, with a strong base, NaOH. All right, and so we're going to then measure how much the temperature rises. All right, and so that's how you would get the delta H value for a acid-base reaction using HCl and NaOH. You can also have a more complicated calorimeter that we do not do in the lab, but you can have one that is a constant volume calorimeter called a bomb calorimeter, because pressure increases quite a bit. So yes, so you have your bomb calorimeter. We are not going to be doing those. We're going to be doing our coffee cup calorimeter. All right, and so this would be a reaction that we could do in lab. We take a piece of zinc, we weigh it. All right, it weighs 35.8 grams. All right, so then we can heat it up. All right, so we could take it from the room temperature at 20 degrees to a higher temperature, 28 degrees Celsius. And then we can say how much heat was required, and the specific heat is given for your zinc. So this is not water, so this is not 1, this is zinc. And so here you just have your equation. Q is equal to ms delta T. And so it says how much heat was required to do this. So we're solving for Q. You need to know that Q is equal to heat. If they ask for heat, they're asking for Q. You have your mass, 35.8 grams. They give you the S value. It is 0.388 joules per gram degree Celsius is what they give you. All right, and so here is where you have your delta T. And again, you can convert both of these to Kelvin and get your delta T, or you can use it in Celsius. Delta T. Delta T is equal to 28.00 minus 20.00. And so our delta T is 8.00 degrees Celsius. All right, so a lot of times when they put this, they will write simply degree, and that is because your delta T can be in Celsius or Kelvin. All right, and we never ever work in Fahrenheit. So if you talk about a degree, we're talking about Celsius or Kelvin. Normally it is Kelvin. The only time we would be talking about Celsius is when it is a delta T. And the only reason why that would be in Celsius is because it's exactly the same as doing it in Kelvin. All right, and so then you see that the grams are going to cancel. So you make sure your units are right. Grams, yes. All right, degree change, yes. Again, it doesn't matter if your degree change is Celsius or Kelvin. And then you just multiply those three numbers and you get the heat required to change the temperature of that amount of zinc from 20 to 28. And so that would be, when you push the buttons, 111 joules. All right, so now we're going to burn something, all right? And we're going to look at a temperature increase, and then we're going to write the thermochemical equation for this reaction. So what we're looking for is delta H. So when we are going to write the thermochemical equation for a reaction, that means we're going to have this balanced chemical reaction, and then we're going to have the delta H. And so we're going to have some information to calculate it. We are going to put our nitromethane. You don't have to know what nitromethane is. They tell you what it is. It's right there. So we put 1.724 grams of our nitromethane in a calorimeter with oxygen, and then we ignite it. Of course, it's going to release energy, all right? And we're going to determine how much heat was released by the temperature change. All right, so we know when it gets hot, temperature increases, it gets hot. This is an exothermic reaction. Anytime your delta T is positive, that means it is getting hot. That means it is an exothermic reaction. All right, and so they give us the heat capacity of the calorimeter. So to find Q, that is, well, it depends. It is ms delta T, and it is also C delta T. It depends on the problem. Did they give us the mass, the specific heat in delta T, or did they give us the calorimeter heat capacity? Well, yes, they gave us the calorimeter heat capacity. So they told us that we're going to get 3.044 kilojoules for each degree Celsius change. All right, so this time we're not given a specific heat and a mass. We're given the heat capacity of our calorimeter. So to find Q, we simply put in our 3.044 kilojoules per degree change, and then we have to calculate our degree change. Well, we simply take our final 28.81, subtract the initial 22.23, and so I should write it on top of each other, 28.81 minus 22.23. All right, so that's a 7, that's a 5, that's 8. And so we have 6.58 degrees Celsius. And again, if you want to convert both of these temperatures into Kelvin and then get your delta T, you will get the exact same answer. All right, so that's how we get our Q. The thermochemical reaction, when you have delta H is equal to Q over N. All right, so the delta H is going to be joules or kilojoules per mole. So Q is just kilojoules or joules. All right, to get the delta H, it's per mole in the balanced chemical reaction. All right, and so we need to then know per mole of our nitromethane. So we have to convert this into moles. So we have to divide by the molar mass. All right, so we got 1 carbon, 12.01. We've got 3 hydrogens, 3.03. We got a nitrogen, 14.01. And we got an oxygen. We got 2 oxygens, that's 32. So we add that up, 0.05. We got 7, 8, 9, 10, 11. 61.05. So we have to take 61.05 grams per mole of the nitromethane. That is N. So here is your Q. Here is your N. In order to get the delta H, you have to take Q over N. Now you have to see, this is the difficult part, when we found our Q, all right, so that gave us a positive number because we had a positive delta H. All right, when we're doing a calorimeter, we have heat gained is equal to heat lost. All right, so that's why we use a calorimeter, a coffee cup. We don't lose any energy, all right? We don't lose any heat to the surroundings. In our perfect calorimeter, all of the heat that was released by the reaction, that heat was gained by the temperature going up at the thermometer. All right, and so heat gained is positive, and that is the heat gained by the calorimeter. And we're measuring the temperature increase and the Q value for the calorimeter. That is the heat gained by the calorimeter. Well, where did that heat come from? It came from the reaction. The heat was lost by the reaction. When you take this Q value, this is the Q for the calorimeter. That's the heat gained. That is equal to the heat lost by the reaction. All right, and so this is the heat gained, but we're looking for this Q value for this reaction. In this case, that is the heat lost, the heat released by this reaction. All right, so the key here is make sure you see that this reaction is exothermic. How can you see it's exothermic? Well, the temperature went up. Anytime the temperature goes up, that means you released heat. That means it is exothermic. And you need to know that that means that you have a negative value for your delta H. For this reaction, the delta H is negative. Why did our delta H become positive? Why is it calculated as positive? We did everything right. Because we are calculating the heat gained by the calorimeter. All right, and that's equal to the heat lost by the reaction. We want the heat lost by the reaction. We want the thermochemical equation for the reaction. And so that is why you get a negative value for your delta H. All right, so here it is all worked out. So so they put the negative here. All right, so heat gained is equal to heat lost. All right, so they put then in the negative, so the reaction, all right, so the difference is the heat gained by the calorimeter. Q calorimeter is equal to negative Q reaction. Negative Q reaction, heat loss. So heat gained, Q calorimeter is equal to heat lost, negative Q reaction. All right, and so when they solve that for the Q for the reaction, you multiply both sides by a -1. And so that's negative the C value delta T. For the reaction, you get a negative Q value. For the calorimeter, you get a positive Q value. So Q calorimeter, that's equal to positive 20.03 kilojoules. So the heat gained by the calorimeter is equal to the heat lost by the reaction. All right, so then we took our mass and we then divide by the molar mass. All right, but they're doing it, they put the mass on bottom. I would get my N by taking the 1.724 grams and dividing by the 61.04 grams per mole. And then I would take that number of moles. All right, and then I would have my Q right there, 20.03 divided by my moles, whatever you get when you take 1.724 divided by 61.04, and then you divide those two numbers. That is what they're doing here. They're just doing it in a different manner. And then your delta H is negative 709 kilojoules. So we knew it was going to be exothermic. A lot of reasons. Temperature went up. It's a combustion. And so this is an exothermic reaction, a negative delta H. All right, but that's not the answer to the question. They better not stop there because the question was to write the thermochemical equation. So now you write the reaction and then you put the delta H is equal to the negative 709 kilojoules. So this is a balanced thermochemical equation. That means you release 709 kilojoules for every 1 mole of your nitromethane that you burn. You release 709 kilojoules for every 3/4 of a mole of oxygen you use. You release 709 kilojoules for every mole of CO2 produced. All right, so it is a balanced chemical reaction. Again, the coefficients do not have to be integers. If it said that this had to be in integers, all right, so if it said make sure that your balanced chemical reaction is in integers, then you see that you would have to multiply the whole thing through by 4. So the whole thing had to be multiplied by 4, but make sure that you also multiply your delta H by 4. And so you'd have 4 CH3NO2s plus 3 O2s yield 4 CO2s plus 6 H2Os plus 2 N2. And now your delta H would be releasing 2,836 kilojoules. So it depends on how you do it. If you're multiplying it by a perfect 4, then you would give 3 sig figs. If you're adding it up 4 times, whatever. So anyway, this would be your delta H. The key is if you're multiplying this through by 4 to get rid of all of the fractions, then you also have to multiply your delta H by that same factor of 4. All right, so now we're going to manipulate reactions to get a new reaction with its delta H. And so Hess's law will tell you that when you add reactions, you add delta H's. So add reactions together, you add the delta H's. All right, so that's all Hess's law is. You add reactions, you add the delta H's. All right, so let's say we wanted to burn some carbon and get carbon monoxide. All right, that is extremely difficult to do in lab. It is extremely easy to take our carbon and burn it with oxygen to get CO2. That is extremely easy. All right. Well, they kind of gave it in the way that they shouldn't give it. It's also easy to get a tank of carbon monoxide and burn it to get to CO2s. This is the way that I would put it. All right. That is very strange. I feel like this data is wrong, but okay. Whatever data is given on the test, use it, whether it's wrong or not wrong. I'm just afraid I get to the next slide and they're going to change something on me. All right, so they're going to give you two reactions and you have to manipulate the two reactions in order to get the overall reaction. All right, well, they didn't. Okay, good. All right, so what I would say is you can take CO and add O2 and get two CO2s, and your delta H is a positive 566.0 kilojoules. So there are a few that do not make sense, and this would be one of them. If you do the complete combustion of carbon monoxide, apparently that is an endothermic reaction, not something that you would predict. All right, so what you do is you take these two reactions and you have to make this one reaction. So you're going to manipulate these two reactions in order to get this, to add them up to get to this reaction. So you see that you need two carbon graphites as a reactant. The only place you see carbon graphite in your given equations is right here. We need two of them. So you're going to take this first reaction and you're going to multiply it by 2. And that will give you two carbon graphites, the only way to get two carbon graphites. Now, oxygen's in both of them, so you can't mess with the oxygens. All right, your two COs. The only place that you see a CO is right here, and it is two of them. In order to get that on the right side, we have to reverse this reaction. So when we reverse the second reaction, your delta H becomes positive, because it was negative. If it's given as negative, you reverse the reaction, it is now positive. All right, so the first reaction was multiplied through by 2. That means we have to multiply the delta H also by 2. We had to reverse the second reaction, and that means we had to change the sign. All right, so when we multiplied the first reaction through by 2, we multiplied the delta H by 2. When we reversed the second reaction, wait a minute. What am I seeing wrong? You don't reverse the second reaction. All right, so scratch that, reverse that second reaction. All right, so we have to have CO as a product, and we already have CO as a product. I'm reversing it because I think this is the way the data should have been given. All right, so the data should have been given this way. All right, because you burned your CO to get your delta H. CO2 does not decompose easily into CO and O2. That is not the data you're going to get in lab. All right, so yes, we reverse this one to get the one they gave us. All right. Anyway, I would not give the product problem as they gave it. All right, so you don't have to do anything to the second reaction because you already have your CO as a product. But if it was given the way it should have been given, you would have to reverse it. All right, so the key is, here is your reaction that you want. So you have to manipulate these two reactions in order to add them up to get this overall reaction. So the way they gave it, you just have to multiply the first one through by 2, then you multiply that delta H by 2. The second one, you just write it down as given to you, and then you add them up. And you will get your overall reaction. I feel like this data is wrong, but fine. Whatever data that they give you, you're going to use it. So the key is to follow the rules. The rules are your delta H's. You add up the two reactions. You have to add these two delta H's in order to get the overall delta H value. All right, so we're going to talk about heat of fusion. All right, so heat of fusion is called heat of melting. So we are taking a solid and going to a liquid. So you need to know that your fusion is melting. All right, So if you look at ice, what do you have to do to melt ice? We have to take it out of the freezer. You have to add heat to it. So you have to heat a solid to make it into a liquid. Every delta H of fusion is endothermic. So every delta H of fusion is going to be positive. So anytime you see a delta H of fusion, that is going to be an endothermic positive delta H value. You can also do the heat of vaporization. What does that mean? That means you're going to take a liquid and convert it to a gas. If you think of water, boiling water, you have to heat the water. So any liquid, you have to heat it to make it into a gas. So every delta H of vaporization is endothermic, a positive delta H value. All right, and then sublimation is when you go from a solid to a gas. The most famous of these, one that you can see every day, you just go down to Hy-Vee and buy some, is dry ice. So that's CO2. It's a solid. That is dry ice. And then it goes to CO2 gas. It's called dry ice because it never goes to the liquid state. It just goes directly from a solid to a gas. All right. And so again, you got to take that dry ice out of the freezer in order for that to vaporize. And so you have to heat your dry ice to make it into a gas. Again, every delta H of sublimation is going to be endothermic. All right, so again, any reverse of this, if you want the liquid to go to the solid, if you're going liquid to solid, all right, so that is just converting, just reversing this reaction right here. If you have liquid going to solid, all right, the heat will come with it. All right, so you have heat here. Now you are exothermic. All of these are endo. All of these are endothermic. If you reverse an endothermic, it becomes an exothermic reaction. So reverse gas. Now you're going gas to liquid. You have to heat the liquid to make a gas, exothermic. All right, so that's steam. So if you ever put your hand over steam, it's very hot. And so it is liquefying on your hand and you have a lot of heat on your hand and you will burn your hand. And then one that's more difficult is the gas to a solid, more difficult because, well, I don't have any examples of that. I don't have any gases that turn directly to a solid and they are hot. So, but if you would, that is an exothermic reaction because you have to heat the solid to get the gas. So anytime you have an endothermic reaction, you reverse it, you have an exothermic reaction. All right, so what is the enthalpy of reaction for the reaction of calcium metal with water? All right, so we cannot do this in lab because it is a very slow reaction. And so here are two reactions that we do have that are easily done in the lab. This is your HCl plus NaOH. We can easily get a delta H of that, negative 55.9 kilojoules. We can take our calcium solid, add acid to that, and we can get calcium ions and hydrogen gas. And we can get that delta H value. So we're going to manipulate these two reactions in order to get this one. So we have to look and see what's constant. All right, so here we go. We got a calcium solid. We have to find a calcium solid. The only place that we have a calcium solid is right here. This reaction, we want one calcium solid and it has to be on the left. So this is going to remain as written because it has the calcium solid on the right side of the reaction. All right, now we come to the next reactant. We need to have two waters. The only place that we have water is right here. It is a product, and we only have one of them. So this reaction has to be reversed because we have to have water as a reactant. So we have to reverse this. All right, but we also have to multiply it by 2 because this balanced chemical reaction says we need to have 2 waters. So we have to reverse it and multiply it by 2. Then we're going to add them up. So that means that we have to reverse this delta H, which means now it is a positive 55.9, and we have to multiply it by 2. And so now we have to multiply the delta H by 2. And so that gives us a 111.8 kilojoules positive because we reversed it. And now we're going to take this 111.8 positive and this negative 543, add them up, and get our overall delta H for this reaction. All right. All right, so we had to reverse this one. So we multiplied it by, we had to reverse it, change the sign, multiply it by 2. There's our 111.8. This one was written exactly as needed right there. All right, so when we do that, all right, do we get the correct reaction? That is the question. We have 2 H pluses as a reactant. We have 2 H pluses that is a product. We subtract 2 H pluses from both sides. It's like a spectator ion. It doesn't show up in the overall reaction. All right, and so you cannot say I have a reactant that is 2H plus and a product that's 2H plus. It cannot be a product and a reactant. It can be a product or a reactant, but if they are both completely gone, then it is not a product or a reactant. It is either a catalyst or an intermediate or a spectator ion. All right, so when you add them up, you get the calcium solid. Yes, you get your 2 H2O liquids, but yes, you also get the calcium plus 2 reactant. You get your H2 product, and you get your 2 OH minuses as a product as well. And when you add those up, you get a negative 431.2 kilojoules. All right, so this is using Hess's law. So this reaction is very difficult to get in lab. These two reactions are very easy to get in lab. So we manipulate these two reactions to get this more difficult reaction to do in the lab, and that is called Hess's law. All right, so we're going to do a lot of stuff with standard enthalpies of formation. So this is your delta H, and there's usually a little circle up here. All right, standard state. So that circle means standard state. And these are not gases, all of them. These are our delta H values. And so a standard state here is 25 degrees Celsius in 1 atmosphere. And then you would put a little sub F for formation. So when you do a standard, the circle there is standard, enthalpies, delta H, of formation, sub F. All right, what we're doing is we are making 1 mole of our product from elements in their natural state. All right, so again, this is read as delta H naught or delta H 0. That is the standard state. Unfortunately, the standard state here is 25 degrees Celsius and 1 atmosphere. So that 1 atmosphere doesn't change. But remember, in chapter 5, we have STP. All right, that is not a circle. That is standard temperature pressure of a gas. When you're doing standard temperature and pressure of a gas, remember 0, 1. When you have STP, you should write 0, 1. All right, what does that mean? 0 degrees Celsius, 1 atmosphere. All right, that is very important. You're going to use that all the time. If you don't know that your delta H naught of formation is 25, it doesn't matter. You're going to be given a chart. It's going to tell you that. You have to know that STP is 0 degrees Celsius and 1 atmosphere. Nowhere does it tell you that. You have to know that. All right, so we are going to make 1 mole of this compound from elements in their natural state. All right, it has to be in their natural state. Carbon is going to be in graphite as its natural state, not diamond. Oxygen is going to be as oxygen gas O2, not as ozone O3. All right, so if you have more than one different form of an element, that is called an allotrope. All right, so you have carbon graphite, you have carbon diamond, you have carbon buckyball, All right, so those are allotropes of carbon. All right, but the one that has a delta H naught formation equal to 0, that is the element in its natural state. And for carbon, that is carbon graphite. For oxygen, that is O2 gas. All right, and those are going to be in a chart. So anytime you're wondering, well, is it O2 or O3? You look at the chart, the one that gives you the delta H naught, a formation of 0, that is the way that that element exists in its natural state. That is the most stable form of the element. All right, so here it is written out for you. This is your delta H naught formation, standard enthalpy of formation. All right, the key here is you have to make 1 mole of the substance, which means you're going to have to use fractions many times. You are going to have to use fractions because the rule is you make 1 mole of the product. Whatever fractions you have to use to make 1 mole of the product, then you use them. If you don't need fractions, fine, but you must have 1 mole of the substance. All right, and they come from elements in their natural state. So if we're writing the delta H naught formation for water, your delta H naught formation for water, that means the elements that make up water. That means hydrogen gas makes up water and oxygen gas. And we produce H2O. All right, so it's not about balancing this reaction. It is about the delta H naught formation, which means you have to know that it is 1 mole. You make 1 mole of the substance. So this is set. That has to be a 1. You can use any other numbers you need to balance it, any other fractional numbers. All right, and so we need 2 H's. Yes, we have 2 H's. We need 1 O. That means we have to use a fraction. We need 1/2 of an O2. The only correct answer for the reaction for the delta H naught formation of water, because by its definition, it is the formation of 1 mole of the substance. This is set. This cannot change. This is 1 mole. You make 1 mole. Whatever integers or fractions you need on the other side, you have to put them in order to balance the delta H naught formation reaction. All right, and you're going to be given table 6.2. There's nothing to memorize on table 6.2. And there's also a table in Appendix C. If table 6.2 doesn't have the substance you're looking for, go to Appendix C, and they have more listed at Appendix C. All right, so here is our reaction, and we want the delta H for it. So the way that we're going to find the delta H for a reaction, you take your delta H naught for this reaction. So you take the delta H naught formation for the products, you add them all up, subtract the delta H naught formation reactants, add them up. So add up all the delta H naught products, add up all the delta H naught reactants, take that number from the products, subtract the number from the reactants, and you will have the delta H for your reaction. All right, so here is table 6.2. All right, so CCl4, it is listed as negative 135.4. So you find your delta H naught formation. Here is your CCl4 on table 6.2. CCl4 is here, negative 135.4 kilojoules. Here is our HCl, 1 mole of HCl, negative 92.3. Negative 92.3 kilojoules per mole. I should put the per mole. Your delta H naught formations are always in kilojoules per mole. Delta H naught formation is in kilojoules per mole. When you're doing the delta H naught formation, though, it says for 1 mole. And so if they just write kilojoules, yes, that is for 1 mole. But if you have more than 1 mole, like you do for your HCl, you have to multiply it by 4 because you don't have just 1 mole of HCl, you have 4 moles of HCl. Then you see your CH4 is at 74.9 kilojoules per mole. And then Cl2 is not listed because that is an element in its natural state. Any element in its natural state has a delta H naught formation of 0. It doesn't take any energy to form that, or it doesn't release any energy to form that. It is already existing in nature. It has a formation energy of 0. All right, so then you take your products, you're going to add them up. You got 1 CCl4, so you got your negative 135.4. You got 4 moles of HCl, so 4 times negative 92.3. Those are your products. You add those up. That number goes here. Minus, you have just 1 CH4, so you just have 74.9. You have 4 times 0. Anything times 0 is 0. So your reactants are very simple. That is the 74.9 kilojoules. All right, so you need to multiply the 92, negative 92.3 by 4, and then your 135.4, get a number for your products. Products minus reactants. That is going to give you your delta H. And when you do that, when you multiply your number here by 4, the negative 92 by 4, it is negative 369.2. All right, so they're doing it a little different. They're doing it by using Hess's law, which is also fine. You're going to get exactly the same answer. And so it is a negative 429.7 kilojoules. All right. So now it says to use the, all right, so we have to write the reaction. So here is a question where you have to be able to write a reaction. All right, and we will pick up there tomorrow. We are out of time. So vaporization, you have to know you're going from a liquid to a gas. You would have to write that reaction.